Welcome to this explainer. Today, we're doing something pretty cool, a massive, highly structured cosmic zoom out. We're starting right here, looking at the exact physical mechanics of the ground beneath our feet, and we'll be pulling all the way back to witness the explosive deaths of distant massive stars. It's a journey from the intimately familiar to the mind-bendingly huge.
Here is how we're breaking it down today. 1. Our spinning, bulging Earth. 2. The dance of orbits. 3. The lunar and Martian frontiers. 4. Humanity in low Earth orbit. And 5. Dwarf planets and dead stars. All right, kicking things off with Section 1, our spinning, bulging Earth, the shape of home. So you probably already know the Earth isn't a perfect, pristine sphere, right? But to really get a grip on its true shape, we rely on a field called geodesy. Basically, it's the rigorous science of measuring our planet's exact geometric shape, how it sits in space, and its gravity field. And what geodesy actually tells us is wild. Because our planet is constantly spinning, centrifugal force causes it to bulge right at the center. It's what we call an oblate spheroid. Because of this geoidal bulge, the distance from the Earth's core to the equator is about 21 to 22 kilometers farther than the distance to the poles. So think about that. If you're standing on a mountain near the equator, you are technically closer to space than someone standing at the North Pole. Now that spinning shape ties perfectly into Earth's two main movements, rotation and revolution. We get our 24-hour cycle of day and night because Earth rotates on its axis. But it also takes about 365.25 days to revolve completely around the sun. And yeah, that extra quarter of a day, that is exactly why we have to throw a leap year into the calendar. You combine that 365-day revolution with Earth's 23.5-degree tilt, and boom, that's how we get our changing seasons. To map out this tilted rock we live on, we use horizontal lines of latitude. And there's a magic number I want you to remember here, 111. The physical distance between each degree of latitude is exactly 111 kilometers. That's, roughly an hour's drive on the highway. It's just a really neat, precise constant that lets us pinpoint literally any location on Earth. Moving right along to Section 2, the dance of orbits. Shifting distances. So nothing in our cosmic neighborhood moves in a perfect circle. Everything travels in ellipses, which means distances are constantly shifting. This brings us to two vital terms, perihelion and aphelion. It is super counterintuitive, but Earth is actually closest to the sun at perihelion, which hits right around January 3rd, and we're farthest away at aphelion on July 4th.
This exact same elliptical rule applies directly to the moon's orbit around us. When the moon reaches its absolute closest point to Earth, we call that perigee. And when it swings out to its farthest point, that's known as apogee. And these shifting distances aren't just trivia. They have tangible physical effects down here. At perigee, the moon visually looks larger in the night sky, which is what we call a supermoon. But at apogee, when it's much further away, the moon's gravitational pull on Earth's oceans actually weakens, which gives us noticeably less dramatic tides. It's a perfect example of how distance and gravity are intimately tied together. Okay, Section 3, Lunar and Martian Frontiers. Humanity reaches out. We are honestly entering a new golden age of space exploration right now. ISRO is pushing some serious boundaries with Chandrayaan-4, which is slated to bring actual lunar samples back to Earth, and that's being followed by Chandrayaan-5, a joint rover mission with Japan. Meanwhile, NASA is getting ready for Artemis 2 in April 2026. They're launching a 4-person crew to orbit the moon. This is a massive, absolutely crucial test for the future of human life support in deep space. And if we look further out to the red planet, the momentum is just as incredible. You might remember ISRO made history with their Mars Orbiter mission, or MOM, becoming the first agency to successfully orbit Mars on their very first try. Well, they're building on that massive triumph with MOM 2. And incredibly, it's expected to carry a pioneering Martian helicopter right alongside a rover. Which brings us to Section 4, Humanity in Low Earth Orbit, our outposts. Before we take our ultimate leap into deep space, let's just look at where humans are currently living and working, roughly 400 kilometers above our heads. The crown jewel of low Earth orbit is, without a doubt, the International Space Station. This thing has been assembling since 1998, and it remains the largest man-made object in space. It's just a massive, peaceful collaboration between 5 major space agencies. Now, to stay in orbit, you have to move incredibly fast, and the crucial number here is 90. The ISS travels at a mind-boggling 28,000 kilometers per hour.
That means the station and the astronauts living inside it complete a full orbit around the Earth every 90 minutes. Imagine watching the sun rise and set every hour and a half. And humanity's footprint up there is only getting bigger. China is actively operating Tiangong, their self-built space station. Plus, India has laid out a really bold plan to build and operate the Bharatiya Antariksh Station by 2035. So we're definitely looking at a multinational future for human outposts in orbit.
All right, Section 5, Dwarf Planets and Dead Stars, the Outer Edges.
Now for our final massive leap to the outer edges of the solar system. And when we talk about this region, we inevitably hit a famous controversy. Considering its fame and its historic discovery by Clyde Tombaugh, why exactly isn't Pluto considered a planet anymore? Well, it all comes down to some strict rules set in 2006. A planet has to do three things. 1, orbit the sun. 2, have a nearly spherical shape. Pluto easily passes those two, but it fails step 3. A planet must clear its orbit of debris, meaning its gravity has to be dominant enough to sweep up or push away other rocks. Because Pluto's orbit is just packed with other icy bodies, it lost its planetary status.
Instead, Pluto is now categorized as the largest dwarf planet. It lives in the Kuiper Belt, which is this fascinating ring of icy bodies beyond Neptune, and it's joined out there by other dwarf planets like Eris, Makemake, and Haumea. Interestingly enough, there's another dwarf planet called Ceres, but that one uniquely sits much closer to us, hidden entirely within the asteroid belt. Finally, let's push entirely beyond our solar system and look at the dramatic, explosive fate of stars. The life and death of a massive star is largely governed by one incredibly specific threshold. That number is 1.44. This is the famous Chandrasekhar limit. It was proposed by Nobel laureate Subrahmanyan Chandrasekhar all the way back in 1930. Basically, this limit dictates that the absolute maximum mass a white dwarf star can hold is about 1.44 times the mass of our sun. If a star exceeds that limit, electron degeneracy pressure fails. The fundamental forces pushing outward just can't resist the crushing inward force of gravity anymore. The star instantly collapses, sparking a spectacularly powerful supernova explosion and leaving behind either a neutron star or a black hole. Which brings us to the end of our cosmic zoom out, and honestly, it leaves us with a truly provocative thought. When you step outside and gaze up into the quiet night sky, how many of those seemingly stable, distant stars have secretly crossed that 1.44 mass limit? How many are already quietly collapsing, destined to become black holes, and are literally just waiting for their explosive light to finally reach us? It really changes how you look at the universe. Thanks for joining me on this explainer. Keep looking up and keep asking questions.